Theorems about roots, 5.5 here. When we talk about solving using rational roots theorem, what we're doing is we are finding all the possible rational roots. Not necessarily the rational roots, but all the possible rational roots, and then we have to go on another step to determine which one are actually roots. So as we look at this, we are finding a rational root. Remember, rational roots are things that we can calculate. Rational roots are factors, and when the factors be integers, and these things, when we go ahead and calculate these, what are the possible rational roots of this equation right here? 3x cubed plus 7x squared plus 6x minus 8 equals 0. And what they have told us in the possible rational roots, what we do is we are going to take the factors of the constant. Take the factors of the constant and divide it by the factors of the leading coefficient. So in this scenario, or in this equation, the leading coefficient is 3, and the constant is negative 8. So the factors of 3 are easy. So that is my leading coefficient, which will be in the denominator. And I know that the factors of 3 are simply 1 times 3, plus or minus 1 times plus or minus 1, and plus or minus 3. Looking at the numerator, though, we're looking for factors of the constant. Now, the constant is 8. So we have to remember that the factors are 8 times 1 is 8, and then 2 times 4 is 8. So we actually have 1, 2, 3, 4 possible factors of 8. So now what we're going to do is we're going to combine them. And we will do that, and what I have done here already looking at it is I'm going to have 1 over 1 is going to be plus or minus 1 over 1. Then I am also going to have 2 over 1, which is going to be plus or minus 2 over 1. Same thing here, I'm going to have 4 over 1, so I have plus or minus 4 over 1, and then of course we're going to have plus or minus 8 over 1. So there's my first set of possible roots, and now I'm going to continue on with the still having the leading coefficient. So I have plus or minus 3. So looking at this, I have 3 is going to be in my denominator. So and what we've done here is we've said, hey, 1 over 3, so we have plus or minus 1/3, 2 over 3, so we have plus or minus 2/3, 4 over 3, plus or minus 4/3, and then 8 over 3, so it would be plus or minus 8 over 3. So those are all the possible rational roots. We don't know which one are the rational roots yet. We would do some form of division or factoring in order to find that out. But right now, that's how I would identify all the possible rational roots. And here, there are 1, 2, 3, 4, 5, 6, 7, 8. 8 times 2 because you have both the positive and the negative. So there are 16 possible rational roots. All right, so let's look at what's next here. As we do that, we're going to work on how to use this rational roots theorem. And as you can see here, I have already done this, but what are the rational roots for this equation? Again, the rational roots theorem calls for you to place the factors of the constant over the factors of the leading coefficient. And I have the factors of negative 6 are going to be plus or minus 1 times 6 and plus or minus 2 times 3. So those are the factors of my constant. Then the only factors of my leading coefficient are going to be 1 times 2. So start doing the grouping. We have 1 plus or minus 1 over 1. We have plus or minus 2 over 1, plus or minus 3 over 1, plus or minus 6 over 1. So here's our first 4 terms. Then we're going to go with 2. We have plus or minus 2 over 1. Well, we already have plus or minus 2, so we don't need to worry about duplication. Then we have plus or minus 2 over 2, which is 1. So we don't have to worry about using that. We have plus or minus 3 over 2, so we're going to add that one, plus or minus 3 over 2. And we have plus or minus 6 over 2, which is also simplified down to plus or minus 3, which we already have accounted for. And somehow I forgot plus or minus 1 over 2, which is 1/2. So these 1, 2, 3, 4, 5, 6, these 12 possible roots. Okay, 12 possible roots. And what I'm going to do is just grab one and see if it works. And in doing so, I have 1. And I've done -1, and as I bring this over here, it looks like I'm doing synthetic division. So again, my synthetic division is set up with the coefficients and my constant, so I am dividing 1, -1, into my polynomial. And of course, using synthetic division, I'm going to use my coefficients, and I'm going to have 2, 1, -7, and 6. So doing the synthetic division, of course, I'm going to bring down my 2, add downward, multiply 2 times -1. It's going to be -2. -2 plus 1 is going to give me a -1. Then -1 times -1 is going to give me a +1. Then I'm going to add downward. -7 plus 1 is going to give me -6. And then I'm going to multiply again. -6 times -1 is going to give me a 6. And therefore, my remainder, these are going to cancel out. My remainder is 0, so I can rewrite this as 2x squared minus x plus 6. This is now factorable, and I was able to do factoring by grouping and come up with some information here, some binomials, and come up with 2x plus 3 times x plus 2. And in doing so, I just need to solve for 0 in order to figure out what those x values actually are. So again, 2x plus 3 equals 0. 2x plus 3 equals 0. And move everything over. 2x equals -3 divided by 2. And then x equals -3/2. Same thing goes for x minus 2 equals 0. Of course, I guess I shouldn't rush. Plus 2 plus 2, x equals 2. So we do have 3 answers. X equals -1, x equals -3/2, and x equals 2. And that is how I find out what my actual rational roots are, or using them. Okay, now we will encounter some things that we are going to call conjugate roots, conjugate pairs, and what we are looking at is, let's see, that if you have something, if you have a root that is 3 minus 2i, it's a complex root, and we are also expecting to have its conjugate, 3 plus 2i, because anytime you're dealing with I, we have seen something in the quadratic of like plus or minus 2i. Well, you can't have just 2i as a root and not have a -2i as a root, because you have a plus or minus. So you're going to get both of those answers. So anytime that you see a complex number, you should expect the conjugate root, and that is also going to go for radicals. If we see a plus the square root of b, you should expect to also see a minus the square root of b, because when we find square roots, we have a plus or minus square root. So those are just some things that we should expect to understand and see. So when I'm looking at this example, it says the cubic polynomial has real coefficients. Great. If 3 minus 2i and 5/2 are two roots of this function, what is the additional root? Well, we should know, again, that they're telling us that we have 3 roots. And if I have right here, if I have 3 minus 2i, I should expect to have 3 plus 2i also. Just because I have 5 over 2 doesn't mean I'm going to have a negative 5 over 2, but I know that my complex roots have to be in opposites, inverse pairs like that. So looking at this next example, and it says using conjugates to construct a polynomial. Well, I know that I have root of 2, so I know that x equals 2. I have a root of 8, so I know that x equals 8. And then this thing, this root right here, I know that x equals 2 minus 3i. And what you should hopefully be kicking into and learning is that this thing right here, I, that means I did the square root. I did the square root of a negative 1 in order to get I. So I should know that if I see this complex number, I'm also going to have 2 plus 3i as a possible solution. So that's what we need to recognize, that we have in turn 4 possible roots. If we have 4 possible roots, by Joe, we should have a y equals x to the 4th function, and really we're going to find out that we do. But just looking at it, that's one of those things that we should be picking up on now. So let's look at what is left here. So it says, what quartic polynomial equation has these roots? Well, quartic tells me 4. So look at this. I've already got 1, 2, 3, 4 roots. But I need to write this polynomial in standard form. So I know that to begin with, I can do, x minus 8, x plus 8 to get my answers. Because, let's see here, I can multiply this out and get this very easily. But my complex roots, on the other hand, I know that I have, so I have x minus 8, x minus 2, x minus that 2 minus 3i. So those are my 2 conjugate solutions. And now all you have to do is do your inverse operations and multiply to get your answers. So I have here, I foiled those 2 expressions out,